So for our next video, we're going to look at angles all around circles. So some of them are inside, some of them are outside. So to begin with, we're going to look at the ones that are inside the circle. All right, so to start with, we got central angles, which are pretty straightforward. They're going to be the ones you like the most. Then we got inscribed angles, angles formed by intersecting chords. And then we're going to look at some inscribed shapes, specifically a right triangle and a quadrilateral. So to begin with, central angles. The best part about central angles is that they are the exact same as the arc that they intersect. Ooh, missed it. All right, so what that means is this central angle A, which is getting worse, I should just stop. My central angle A, if I were to call that X, that means that my arc here is also X, right? So X degrees, okay? And if you remember, our arcs are all gonna add up, and going all the way around the circle, they're gonna be 360 degrees. Same thing with the angles inside the circle, right? They're gonna add up to 360 degrees, which is why the central angle is the same as what we call the intercepted arc, or the arc that it opens up to, right? So for examples, we've got this circle here with my central angle being 42, and I want to find M. It's very straightforward, 42 degrees. Okay, central angles are good angles. We like them. Okay, but in order for it to be a central angle, it's got to have this dot, right? They're going to add that dot in there to let you know. They always add the dot to show the center of the circle. All right, now for the second one, it's a little bit different, right? I'm looking for P over here, but I'm given that this arc is 50 degrees. Okay, well, because that arc is 50 degrees, I also know that this angle in here is 50 degrees. And then you got a couple of ways of looking at it. Okay, to start with, this chord here goes through the center of the circle because that dot right there. That means that it's a diameter. That means it cuts my angle or my circle in half, right? So one way of looking at it is that this arc all the way over here is half the circle, which is 180 degrees, right? And this angle here is also 180 degrees because it's a line. So you could say 360 minus 180 minus 50, and that's going to give you P. Another way of looking at it is on the opposite side here. If I have 180 degrees on the right side, that means I have 180 degrees on the left side, which means I could skip all that and say that to get P, I'm just going to subtract 50 from 180. And then, oops, we get that P equals 130. Okay, so central angles are the same as the intercepted arc. Inscribed angles. If something is inscribed, that means that the vertex is on the circle, right? So here I got this vertex B. It's on my circle, right? So it's a little different. Here's the center of my circle at O. Here's my vertex on the circle. If I call this angle X, right? This X is not going to be the same as my intercepted arc here in red, right? Because if it was a central angle, it's the same. This angle is actually going to be smaller. If you can imagine drawing your central angle here, this is definitely a lot wider than this angle X. All right, so get rid of those lines. The specific relationship is that it's half, right? So your inscribed angle is half of that arc that it intercepts, right? So that means if this angle is X, my arc has to be a 2X, right? So if I'm given the inscribed angle, I can double it to get the arc. If I'm given the arc, I can cut it in half to get the angle. So for my examples over here, right, I'm given that my inscribed angle here is 75, and I want the arc. So that means that this is half of the arc, so Z is going to equal 75 times 2, or 150 degrees. Okay, down here, this one looks a little bit different. And I put it in here on purpose because just because it visually looks different than this typical inscribed angle doesn't mean it's not an inscribed angle. Because if I look here, right, this angle, my vertex, whether I could do the angle on the right side or the angle on the left side, the vertex is on the circle. So that means it's an inscribed circle. And I did not put a letter here. Let's call this one, I don't know what I didn't use. I'll call it E. I don't think I used an E. All right, so if I want to find E down here, this is my inscribed angle, right? Well, I know that it opens up to this arc, right? It looks kind of weird because it's, only touching one side, it looks like. But that means that this arc here is going to be 2E, right? And then over here, I know that this big arc is 200. that tells me that 200 plus the 2e has to give me my entire circle, which is 360 degrees. All right, so I could say that 200 plus 2e equals 360. All right. Then if I subtract the 200, we get 2e equals 100, and then divide by 2, and we get e is 80 degrees. All right, so it's still an inscribed angle, it's just another way of looking at it. Okay, angles formed by intersecting chords. All right, so chords have are segments with endpoints on your circle. Okay, a specific kind of chord is your diameter, but it's not always have to be your diameter. Okay, so here I'm just given two chords that intersect. Right, if you think back to Math 2, these angles are the same. They're congruent because they're vertical angles. So if I want to work with these angles, I'm going to call it X. Right? I need to work with my arcs that they intercept. Oop. Oh, tried. All right, so these arcs, right, where they intercept, help us find X because X is the average of those arcs. So I'm just going to call these arcs little a and little b, all right, just to name them. And then let me change colors to something that we can see. X is going to be the average of arc A and arc B. The average, you add everything together and divide by how many you have. So that angle X is going to be A plus B divided by 2. All right, then by the same kind of process, these angles are the same because they're vertical angles. So if I call one of them Y and I call these arcs C and D, we can say that Y equals C plus D divided by 2. So it works in both directions. You just kind of have to go based on what you're given. Like sometimes it might ask you for Y, but only give you A and B. So you'd have to find X and then subtract it from 180 because X and Y make up a line, 180 degrees. All right, so for our examples, over here I'm looking for B, right? And B is that arc or that angle formed by intersecting chords. So it's going to be the average of my arcs. So B is going to equal 45 plus 125 divided by 2. Well, 45 and 125, let's see, it gives us 170, right? And we divide that by 2, and we get 85. So B is 85 degrees. All right, for the second one, it's a little bit different. I'm given the angle on the inside, okay? But I can still write the same type of equation. I'm just going to use my variable in a different spot, right? So normally we would say that angle on the inside equals my arcs added together divided by 2. So that would be Q plus 130 divided by 2. Well, I know what the angle on the inside is, so I'm going to go ahead and plug that in. So now instead of B equals, I know what that is, so I'm going to say 110 equals Q plus 130 divided by 2. All right, so then I can multiply by 2. So we get 220 equals Q plus 130, and then I can subtract the 130, right? And we get 90 equals Q. Nope. Yep. Trying to do it in my head, struggling. All right, so Q equals 90. An inscribed right triangle. So before we talked about an inscribed angle where your vertex was on the triangle or on the circle. Well, an inscribed right triangle means that all of your vertices are on the circle. So here I have A, B, and C all on the circle. So that means this is an inscribed right triangle. It's kind of like the biggest triangle you can fit inside that circle. But specifically, I'm working with a right triangle or the diameter. Right? So this one's more of like a theorem. I'm going to do like a lot of abbreviating here instead of writing it out. But if I'm going to be working with a right triangle, okay, there is a relationship with the fact that the hypotenuse is your diameter. Okay, and that relationship is if I'm told that it's a right angle, so if I'm given that box in the corner, that tells me automatically it's going to have the hypotenuse as a diameter. Okay, or if I'm told that the hypotenuse is the diameter, that tells me that it's automatically got to be a right triangle. Okay, and this is what we call IFF, if and only if, because it works both ways. Right, so if I'm told that it's a right triangle, so if I'm given the box, that means that this has to be my diameter. That's got to be the center of the circle on there. Okay, if I'm told that the hypotenuse is a diameter, so if I'm given that this is a diameter, I know that this is going to be a right angle. Okay, so it goes both ways. So for our first example here, I'm looking for this arc in, right? And I'm told that this is a right triangle. Because this is a right triangle, I automatically know that this segment here has to be a diameter. And because that's a diameter, it cuts that circle in half, which means that n is half of 360, or 180 degrees. All right, for the second one down here, I'm told that this is a diameter because the center of my circle is on that line. So I know that this is a diameter, which means that my angle across from that has to be a right angle. So now this is a right triangle, right? And if this is a right triangle and I have a 30 degrees here, that means that I have a 30, 60, 90, because I have to add up to 180. Right? And then this angle over here is an inscribed angle that opens up to W, which I'm looking for, right? Which means W is double that angle over here, the inscribed angle. So that means W is 60 times 2, or 120 degrees. Okay, so if it's a right triangle, you know there's got to be a diameter. If you know there's a diameter, you know it's got to be a right triangle. It works both ways. An inscribed quadrilateral. Quadrilateral is a four-sided polygon. So if it's inscribed, that means that I have my vertices on the circle. And what we know about our inscribed, oops, let me change to blue, our inscribed quadrilateral is that opposite angles are supplementary. So I'm going to put lowercase letters here. So we got these guys. And so I can say C plus E equals 180. And D plus B equals 180. Because if I know that I have a quadrilateral that's inscribed in my circle, opposite angles are supplementary. So they add to 180. I mean, you can kind of figure that out too. Same thing with the inscribed triangle. You can kind of figure that out using what we know about angles and the arcs. But if you think about this angle C, it opens up to this arc over here. Then angle E opens up to this arc over here. And together, those arcs make up the entire circle, which is 360 degrees. But because these are inscribed angles, because my vertices are on the circle, that means that they're going to be half of the entire circle, or half of the entire circle is 180 degrees. All right. So for example, okay, throw a little mix in here for us. I want to figure out X and Y over here, right? But I'm given expressions, not really, measures of the angles. So I'm just going to write an equation. Okay, I know that over here, this looks kind of like C and E, and we said C plus E equals 180. I can write that equation. So we can say 2y plus y equals 180. All right, those are my opposite angles. So 2y plus y is 3y. So 3y equals 180. Divide by 3, and y equals 60. All right, and then I can do that again for my x's. They're opposite angles, so I'm just going to write it out. Add them together. They have to equal 180. 8x and 2x is 10x. 13 and negative 3 is 10. Subtract my 10 and divide by 10, and we get x equals 17. Okay, so opposite angles are supplementary add to 180. If I'm given an expression instead of a number like 42 degrees, I'm given 8x plus 13, write it out just like you would normally, right? Plug in, write out your equation, combine like terms, and solve. All right, for the second example here, I'm looking for F. Well, F is an inscribed angle that opens up to this angle, or to this arc. So I could figure out what that arc is, right? Or I know that I have this angle over here that opens up to the numbers that I'm given. Either way works. It just depends on how your mind works. So I'm going to go ahead and add these together, right? So I'm going to say that this inscribed angle here is going to be half of whatever the sum is over here. Well, 96 plus 102 divided by 2, right? That's going to give me 198 divided by 2. All right, and let's see, that should be 99. So that means this angle right here is 99 degrees. Right, well, I know that F and 99 are supplementary because they're opposite angles. So we can say F plus 99 equals 180. Subtract the 99. Right, so that's going to give me 81. So F is 81, right? With circles, there's different ways of looking at it. Just go with whatever comes to mind first. They're kind of like puzzles. All right, outside the circle. Okay, so now I got angles formed by two secants and angles formed by two tangents. Remember, a secant is kind of like an extended chord, right? It goes through the circle. A tangent never actually goes into the circle. It is touches at exactly one point and stays outside of your circle. All right, so to begin with, we got two secants. So these are now working with angles that are outside, right? So if I'm looking for this angle, we'll call it X, right? And I'm given these arcs. Now it intercepts two arcs now because it's outside the circle coming through. So if I call my arcs, we'll say A and B. The relationship between A and B and this angle on the outside, right, is that instead of adding like we did with our chords, we're actually going to subtract. All right, so it's going to be the working from the outside, so work farthest away and get closest to your angle. We're going to take the bigger arc minus the little arc and divide it by 2. So X is going to be B minus A divided by 2. Okay, and again, secants are similar to chords, right? If I were to kind of erase this part on the outside, I'm left with two chords. Right, so it's going to be similar in nature when we write our formula. So for two chords, you added and divided by 2. For two secants, you subtract and you divide by 2. And you always work from the outside closest to your angle, right? So bigger minus smaller equals the angle out here. Okay, so for examples, I've got this A that I'm looking for. So that's going to be my angle. So I can say that A, let me find a spot to write, equals the outside minus the inside divided by 2. Okay, well, 88 minus 26, let's see, that would be 66 divided by 2. So then A equals 33. So big minus little divided by 2. All right, now over here, I got some expressions again. Same idea, just write your equation, combine your like terms, and solve. So here I'm solving for D. All right, so I'm going to start with the outside. So we can say 4D plus 9 minus the inside. Now, if I'm using subtraction, you got to use parentheses. All right, that divided by 2 has to equal the angle on the outside, which I don't know that either. It's just an expression. But now I have an equation and I can solve. All right, so I'm going to start by multiplying by 2. Get rid of that ugly fraction. And at the same time, I'm going to go ahead and combine my like terms. Now, the reason that you have to use a parentheses with your subtraction is because this negative has to be distributed through. Because I'm not just subtracting D, I'm subtracting D plus 7. So this ends up being minus D minus 7. All right, so 4D minus D is 3D. 9 minus 7 is 2. And then 2 times 2, not negative, times 2, D plus 10 is 2D plus 20. All right, I'm going to subtract my 2D over, so I get D plus 2 equals 20. Subtract the 2, and we get that D equals 18. All right, set up your equation using your formula, even if it's expressions instead of just numbers by themselves, and solve for whatever variable you're looking for. All right, last relationship for this video. Okay, we got two tangents. So here I got two tangents on the outside. We actually have two ways of looking at this. Okay, so the first one is this is an angle on the outside, just like with our secants. It has the same relationship as that what we just did with our secants, right? So if I call this arc over here A, well, let's use different ones since we already used A and B. Let's say that this is X, and this arc over here is Y, and I'm looking for P. All right, I can do outside minus inside divided by 2. So one relationship is that P equals X minus Y divided by 2, just like we just did. But there's also another relationship. Because I'm telling you that CD and CB are tangent, that means that if I draw a radius to meet the point of tangency where the tangent touches, that's going to be a right angle, right? Because your tangent line always forms a right angle with the radius at that point, right? So because of this, now this like kite looking shape, right? A kite, okay, it's not really a kite because I got two right angles, but it looks like a kite because it's a quadrilateral, right? And I know that opposite angles in my quadrilateral are going to be supplementary. Now, the reason that they're supplementary in this case, right, specifically, not always in a quadrilateral are they supplementary, but these two angles are 90 degrees, which means they add up to 180, and that only leaves us with 180 for right here. Now, because of what we know about our central angles and the arcs, if this arc here is y, this angle here is y. They're the same. So if I'm giving you the angle in here or the arc, it doesn't matter, right? I know that that angle y or arc y is going to be supplementary with p, right? So then my other option is that p plus y equals 180. And again, whatever comes to mind first, whatever information you're given, just go with what you think is easiest at the time. So here I'm looking for t, that's on the outside. Okay, I'm given this 250, right? If this is 250, that tells me that this arc here, right, I can figure out by doing 360 minus 250, right, which is going to be 110. Right, which I did not do a very good job of these problems because they ended up being the same. But I have this 110, so I'm just going to use what we did before with the secants. So we could say that t is going to be the big arc minus the little arc divided by 2. Okay, so 250 minus 110, that's going to be 140 divided by 2. So t is 70 degrees. Right, and then down here, let's see, I'm going to fix that. We're going to change this one. All right, this isn't going to be 110. We're going to make it, I don't know, we'll get rid of this guy. We'll make it 100. So it'll be a little bit different. Not the exact same problem, but close enough. All right, so here, based on what I'm given, just because of the way it's drawn, I'm going to use my second option here. I know that this 100 and k are going to be supplementary. So I could say 100 plus k equals 180. To get k by itself, subtract 100. So k is 80 degrees. Okay, but again, it just depends on how you see it when you start working on these problems. Just go with whatever comes to mind first, and as long as you use the correct properties and relationships, you'll still come to the same answer.